Let's explore the trigonometric functions that are created by manipulating angles on the unit circle. We're going to look at those trigonometric functions in detail. Okay, we're going to take a look at how the trigonometric functions come to be. Now, for many, many years, folks had used trigonometry to solve measurement problems using sine, cosine, and tangent and right triangles. But it wasn't until about the 1600s that they started to understand that these things actually had patterns that became functions. And that periodic nature of trigonometric functions allowed us to model so many things that are going on in the universe. Things like light, sound, even quantum particles at the lowest levels of the universe. Now we could model them. So let's take a look at how that comes about from the unit circle. You can see the unit circle over here on the left of the screen. What I'm going to do is I'm going to start changing the angle, and you're going to see little right triangles start to form. And what's happening now is we're creating the sine graph from that opposite side of the right triangle as the angle is changing and it's going around the unit circle. You can see we're at 66 degrees now, moving on to 90 degrees. And you can see what's happening. We're actually seeing the sine graph being created here. And on the x-axis here is the actual angle, and the y-axis is the value of the opposite side of the right triangle that's formed at that angle. Now we're even more than 180 degrees, and you can see the sine starting to go negative. It's going negative because the opposite side is on the negative part of the y-axis. And when we get 270 degrees, or 3 pi over 2, you're going to see it start to go from its minimum of -1. It's still negative, but it's getting closer and closer to 0 as the opposite side of that triangle gets smaller and smaller. So what we've done is created the sine graph. Let's look at the pattern of the sine graph. At angles between 0 and 90 degrees, it starts at 0 and goes on up towards 1. And on its way, it goes through values of 0 at 0 degrees. At pi over 6 radians, it gets a value of a half. Then it moves up to square root of 2 over 2 at pi over 4. Then to square root of 3 over 2 at pi over 3, and then on up to 1. It repeats the pattern in reverse after pi over 2, or 90 degrees. It starts to go down in the reverse order as before. Square root of 3 over 2, square root of 2 over 2, a half, then 0. And same thing occurs going from pi, or 180 degrees, all the way out to 360, or 2 pi. We're going through that 1/2, square root of 2 over 2, square root of 3 over 2, and 1, but on the negative side, all these are negative values, then we're going in reverse from -1 to negative square root of 3 over 2, negative square root of 2 over 2, negative a half, all the way to 0. Let's take a look at the pattern the sine function makes and put some specifics to it. And if we look at the sine function as a function, graphed out, just like you saw in that animation, this is what occurs, at least in the first the range from 0 to 2 pi. As it turns out, you're going to find out later, this thing continues forever. But in that first 0 to 2 pi, or 0 to 360 degrees for theta, this is the pattern that occurs. And it has a domain of any real number. We can put any value we want in for theta, and sine is always going to we are always going to be able to take the sine of that. And the output, the range, is going to go between a maximum of +1 and a minimum of -1. So what we see on the unit circle matches up with the actual function that's created. Now let's do the exact same thing with the cosine function. We're going to run the same simulation, and you're going to see that right triangle being formed, and now we're looking at the adjacent side of the right triangle. And it started off at 1 because it started off at the point 1, 0, but it's getting steadily closer to 0 as the angle approaches pi over 2, or 90 degrees. Now that it's 90 degrees, it reaches 0, and it starts going negative. And the reason for that is the angles are starting to go to the left on the x-axis. Once it gets down to its minimum at pi, or 180 degrees, it's still negative because we're still on the left-hand side of the x-axis, but it's getting less and less negative as it approaches, as this value gets smaller and smaller and approaches 0. And it's going to reach 0 at 3 pi over 2, or 270 degrees. And now we're looking at that adjacent side. It's getting larger and larger in the positive direction, going from 0 all the way up to 1. So now we've made a complete cycle of the cosine graph, and you need to commit this to memory just like you did the sine version as well. And I'm going to throw the sine one up. The blue is the sine curve and the pink is the cosine curve. It really would be good to commit both these to memory. The sine curve, it's kind of like a roller coaster going up, then down, then back up again. And then the cosine curve, which we just looked at, which starts at 1, it's like a big valley, goes down to 0, then through 0 to -1, then on its way up to 1 through 0 again. Now let's analyze the cosine graph as well. Again, it starts off at a value of 1 when theta equals 0. That's because it's all adjacent and no opposite at that point. Steadily decreasing down to pi over 2, continuing to decrease to its minimum of -1, increasing the rest of the way from pi to 2 pi. Its domain, as with the sine function, is all real numbers. You can put any angle, any value you want in for theta, and it will always give you a cosine. The range, the output of the cosine function, what it puts out is between 1 and -1, very similar to the sine function. Now let's look at the patterns that we've talked about, and you've probably explored these patterns, but we'll go ahead and discuss them again. And this is the values for sine, cosine, and tangent in the first 90 degrees or pi over 2 radians between 0 and pi over 2. Sine increasing from 0 through 1/2, square root of 2 over 2, square root of 3 over 2, and 1. Notice the patterns here. Really, if you think of it in terms of over 2, it's square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and the square root of 4 over 2, which would be 1. This pattern repeats itself throughout the trigonometric functions of sine and cosine, either increasing or decreasing. Sine happens to be increasing in that first pi over 2 or 90 degrees. Cosine does the opposite. It starts at 1 and goes down. 1, square root of 3 over 2, square root of 2 over 2, 1/2, and 0. If you remember those patterns, if you remember that overall pattern of increasing and decreasing those same numbers, it will really help you learn how these trigonometric functions work. Tangent is the ratio of the sine over the cosine, and in quadrant 1, the tangent is always increasing. It goes from 0, because it's 0 over 1, to the square root of 3 over 3, to 1 at 45 degrees or pi over 4, where the two legs are equal. At pi over 3, it goes up to square root of 3, and then it increases very rapidly after that to reach a value of undefined, because at 90 degrees or pi over 2, it's actually 1 divided by 0, because it's all opposite and no adjacent. If you remember this pattern in quadrant 1, it's going to help you enormously in terms of being able to figure out ratios in other quadrants. Now, if we take these values and plot them on the tangent function, where the input is theta, the angle, and the output is the value of the tangent of the angle, we see some pretty interesting different patterns. Tangent behaves quite differently from sine and cosine. It has a value of 0 at 0 because tangent, again, remember, is sine over cosine, and the sine is 0 at 0. But then it increases slowly at first, and then very, very rapidly as theta approaches pi over 2. In fact, at pi over 2, it has a vertical asymptote, because as it approaches 90 degrees in pi over 2 radians, the sine over the cosine becomes very, very high, because the cosine approaches and then gets to 0. Once the cosine is 0 at pi over 2, we have 1 divided by 0, so it becomes an undefined value. And then that pattern repeats itself. So at just beyond pi over 2, it goes from negative infinity and increases all the way up to 0 at pi, and then increases again to positive infinity at 3 pi over 2. So it's undefined at pi over 2, at 3 pi over 2. In fact, at every odd multiple of pi over 2, 1, 3, 5, 7, negative pi over 2, negative 3 pi over 2, and so on, it is undefined at odd multiples of pi over 2. An interesting thing about the tangent function is it's always increasing over its cycle. And it has a cycle. Over that cycle, it goes from negative infinity, where it's undefined, through 0 to positive infinity. And then it repeats that cycle over and over again. And that's all because tangent is the ratio of the sine to the cosine. So let's talk about range, domain and range. So domain, what can go into the tangent function? Unlike sine and cosine, there are certain values we cannot put into the tangent function. And that's wherever the tangent's going to wind up being undefined. And that, since tangent again is sine over cosine, that's where the cosine is 0. So the cosine is 0 at pi over 2, 3 pi over 2, odd multiples of pi over 2. Tangent is undefined. It cannot exist. So those are values that are excluded from the domain. So we say that the domain of the tangent function is all real numbers except odd multiples of pi over 2. Now the range, however, instead of being a defined range between 1 and -1, like the sine and cosine, tangent has an unlimited range. In fact, over one cycle, like this cycle that starts at pi over 2 and ends at 3 pi over 2, it goes from negative infinity, where it's undefined, all the way up to positive infinity. So the range of the output of the tangent function is all real numbers.